Welcome back to Integral Calculus. In this video, I want to go through some tests of convergence. The ideas in this video on their own tended to sit a little bit uncomfortably with students. I'm going to go through what is quite frankly a fire hose of information, a couple of tests that we can use that will tell us whether or not a series is going to converge, but no other information. Much like the absolute convergence of an alternating series, the ideas here are going to tell us that the series converges, but give no indication of what the limit is going to be. It, in a sense, feels incomplete. And where we are, it is incomplete. It's something that we're going to be filling in a little bit later. In coming lessons, we're going to learn how to construct a series that, where it converges, will converge in a very predictable way, but it will not converge everywhere. So understanding how, when, and where that sort of a series will converge is interesting in its own right, and these ideas are going to come back for that. Moving forward in the study of mathematics, that is something that comes up in a lot of different applications, where we know that we can construct a series, and if the series converges, then this, that, or the other good thing is going to happen. But on its own, as an introductory term, this feels weird, and it feels like you're missing something until we get to those later points. I promise you're not missing anything. It is kind of a half step or a half measure. The first test that I want to look at is a p-series. This is another special class of infinite series that is relatively well studied. The sum k goes from 1 to infinity of 1 over k raised to the p power. In a sense, this is kind of the reflection of the geometric series where we had some base r raised to the k power. In this case, it is the exponent that is constant. So this is a reciprocal of polynomial powers. But if that p is bigger than 1, the p-series will converge. If p is equal to 1, then you have the harmonic series, which I've already mentioned, does not converge. And if p is less than 1, then it also will not converge. The comparison test I referenced when I first introduced the harmonic series a couple of videos ago. If you have two series, and one of them you know things about, the one you know things about, we're calling bk here. Right? Up here we know that bk converges, down here we know that bk diverges. If you can construct a comparison so that for every entry in the series you can compare them, that gives you the information that you need. And coming back up here to the p-series itself, we can see how these comparison test was implemented in the p-series. Right? If you consider the case of p equals 1, then you just have the sum 1 over k. So you have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. If you pick a value of p bigger than 1, say 2, then you have 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 and so on. Right? 1 over 25 is smaller than 1 over 5. 1 over 36 is smaller than 1 over 6. In the smaller case, your new series also converges. In the bigger case, right, if we choose something like p equals 1/2, well, 1 over the square root of 1 is 1. 1 over the square root of 2 is something like 0.7. 1 over the square root of 3 is something like 0.4. 1 over the square root of 4 is 1/2. In each case, right, 1/2 is bigger than 1/4. 1/3 is bigger than 1/9. So we had a divergent series to start. We found a new series where every term is bigger, so the new series also diverges. The comparison test almost always compares back to something like the p-test or the geometric test. So as a quick example here, if I have something like the series, k goes from 1 to infinity of 1 over 1 plus 2 to the k. Well, I know that 1 plus 2 to the k is bigger than 2 to the k by itself, which means that 1 over 1 plus 2 to the k is smaller than 1 over 2 to the k. And I know that 1 over 2 to the k is a geometric series that will converge. So I have a converging geometric series, and I have a series that I'm thinking about where every term is smaller than the corresponding term in the geometric series. I have no idea what it is going to converge to, but I know that it does converge. Up next, I have the root test, which is one of the strangest looking tests that I've come across in any branch of mathematics. If we have an infinite series, sum on ak, we're going to take the limit as k goes to infinity of the kth root of ak. We're going to call that limit rho. If the limit does not exist, we have no hope. If the limit does exist and the limit is smaller than 1, right? Every mention of this test includes this 0 over here, but that's actually a requirement because I wrote the test down wrong. There is supposed to be an absolute value on that. Right? So we have to take the absolute value of the argument, and once we have done so, then we are guaranteed this limit is going to be positive. You don't even need to worry about having the possibility of it less than 0. But if this limit is less than 1, the series will converge. If this limit is greater than 1, the series will diverge. If this limit is equal to 1, then we don't know. There is no conclusion that we can possibly come up with. Or I guess we need a different test to try. So the root test generally shows up in cases where you have weird exponents. So something like the sum k goes from 1 to infinity of n squared plus 3n over 4n squared plus 5, the whole thing raised. Oh, I switched between n and k halfway through writing that down. Sorry about that. Those are all supposed to be k's, right? So k squared plus 3k over 4k squared plus 5, the whole thing raised to the k power. So if I take the kth root of ak, I just get the stuff inside, right? There's a k power out here that I can now ignore. and then I can take the limit of that as k goes to infinity and use my results there to figure out what's happening on the original series. That is an incredibly corner case. I have seen in my life 3 times where I've found the root test to be useful outside of teaching the root test or being a student in a class where my professor taught me the root test when I was taking calculus. But it does exist, and so I've mentioned it. The last test that I want to talk about in this video is called the ratio test. All right, so for any infinite series, sum k goes from 1 to infinity of ak, we're going to take another limit. This time we're going to take the limit of the absolute value of the ratio of 2 sequential terms. So ak plus 1 over ak. We're going to call that limit rho, and it's actually the same conditional test as for the root test. If rho is less than 1, the series converges. Every description I've ever come across includes that 0, but it's not actually necessary because there is no way for rho to ever be negative. If you get that rho is negative, that means you did the test wrong. All right, but if the limit is less than 1, the series converges. If the limit is greater than 1, the series diverges. If the limit is equal to 1, the ratio test is inconclusive. The ratio test is incredibly powerful in a type of series called a power series that we're going to be studying extensively in the coming lessons. But for right now, I'm just going to give you how about the sum k goes from 1 to infinity of x to the k over k factorial. If it's been a while since you've thought about factorial, it's one of those things that shows up every now and then it doesn't show up again until you have completely forgotten how it works. Remember that in general, n factorial means the product of 1 times 2 times all the way up to times n. So if I want to take 7 factorial, that means 1 times 2 times 3 times 4 times 5 times 6 times 7. And if you plug that into a calculator, you get 5,040. I happen to know that offhand because, well, I taught a class where 7 factorial showed up about once a week. There is no value to knowing that offhand, and if I'm really lucky, that's actually not the value and I've already forgotten it, but probably not. Another interesting thing about the factorial is that you can define a factorial recursively. So n plus 1 factorial is n times n factorial. I'm sorry, n plus 1 times n factorial. Because if you expand out that n factorial, you'll have n plus 1 times n minus 1 times n minus 2, all the way down to times 2 times 1. So why write out all of that stuff when you could have just written this as 7 times 6 factorial? That's what we're talking about here. And so if I want to think about, in this particular example, ak is x to the k over k factorial. Then a k plus 1 is x to the k plus 1 over k plus 1 factorial. And I can rearrange that. X to the k plus 1 is x times x to the k. K plus 1 factorial is k plus 1 times k factorial. And once I realize that, then when I set up my limit, rho is the limit as k goes to infinity of a k plus 1 over a k But now if I multiply both of the top and bottom of the big fraction by k factorial, it will cancel out those two k factorials. And if I divide top and bottom of the big fraction by x to the k, it will cancel out both of those x to the k's. And so we're left with the limit as k goes to infinity of x over k plus 1. This is going to go to whatever x is over infinity, and, well, that's equal to 0. And that is enough for me to conclude that this series converges. Once again, I don't have a clue what it converges to, right? I have not evaluated the series. I haven't taken the limit on the sequence of partial sums in order to tell you what the value of this series is. And for a lot of people, that's disappointing, disheartening, feels empty in some way, shape, or form. And so I want to reiterate that the value of these tests is a check of another derivation. You have done some work and you've come to an infinite series that should give you the values that you need for the problem at hand. But you're not sure if the series actually works, right? Somewhere in that process is a step of, if the series converges, then you can do this. And you just assumed, well, I assume the series converges, so I'm going to do that. Then you have to go back and check and say, well, did it actually work? These power series that we're going to be talking about in upcoming videos, one of the interesting things there is that the value of x is an unknown. And for certain values of x, certain power series will or will not converge. For now, though, let's just end this with a little bit more practice on tests for convergence. And I'd like you to take a look at the sum k goes from 1 to infinity of n cubed over 3 to the n. There are a couple of different tests that will let you know whether this series converges or diverges. I specifically want you to try using the ratio test as a chance of practicing that process. Take a couple of minutes, see where you can get to with that, and I'll see you in the next video.